Treat this episode as a diagnostic. Where are you structurally slow to adapt? Welcome to AI on AI, where smart systems dissect smarter systems live. Today we're tackling agentic robots, vision language action models plus embodied reasoning, and why that matters for the enterprise.
The big shift is robots that think before acting, interleaving language reasoning with motor commands. It's like giving them headlights on a foggy road, clarify intent, then move safely.
And strategically, the stack is splitting into orchestrator versus action model. One plans with tools and context, the other executes low-level motion. Clean separation reduces brittleness and speeds iteration.
Recent releases show multi-embodiment training with a motion transfer mechanism. Skills learned on one robot can zero-shot transfer to another. Think choreography that travels across bodies, not just steps memorized.
Technically, embodied reasoning has leveled up. Complex pointing, progress estimation, and multi-view success detection. Measure twice, cut once applies, verify where, then act.
Evaluation Titan 2, rank consistent sim tests in an open-source physics engine before hardware A/B runs. It's the wind tunnel before the highway, saving cycles and broken grippers.
Contrarian view, not every task needs thinking traces. For tight reactive control, a clean policy may outperform deliberation. Overthinking is, debugging spaghetti code in the dark.
As long as the robot doesn't cook spaghetti while debugging. But seriously, thinking helps when tasks branch or recover from errors.
Let's ground this in use cases. What's landing in production?
Warehouse bin picking with variable lighting and clutter, plus tray sorting, embodied reasoning improves success detection and reduces reruns. Good input, good output, good feedback, better output.
Retail inventory inspection from messy shelves to backroom audits. Orchestrator parses images, points to gaps, and drafts a restock plan. Less where S Waldo, more here, S exactly what's missing.
Home services packing a suitcase from a checklist and weather. The planner retrieves context, the action model decomposes motions. Like chess for planning, Jenga for execution, don't topple the stack.
Kitchens are great stress tests. Sorting recyclable items versus compost, handling slippery containers, and recognizing progress. Multi-view cameras boost reliability.
Hospitals supply restocking and tray delivery with spatial constraints. Safety where pointing steers away from fragile equipment. Progress markers ensure tasks finish, not just start.
Building on Expert 4's point, multi-view helps, but latency can bite. If success detection lags, you get stale signals. Real-time thresholds and adaptive token budgets mitigate that.
Write, fail fast, learn faster applies. The system modulates thinking budget, more for video QA, less for precise points. It's cognitive cruise control.
Motion transfer seems pivotal. How exactly does it generalize?
The training aligns trajectories and affordances across embodiments, extracting shared structure. Think grab the handle as an affordance, not move servo 11 by delta.
Data scarcity shrinks when communities contribute diverse robot logs. Network effects kick in, more heterogeneity, stronger generalization.
Pushing back slightly, alignment across vastly different bodies is harder. Humanoids versus tabletop arms have huge gaps. Transfer helps, but fine-grained dexterity still needs targeted data.
Agreed, but even modest transfer bootstraps skills and reduces post-training. Then specialized fine-tunes add dexterous polish.
Don't forget simulation scaling. Rank consistency means we can explore architectures fast, then confirm on hardware. Prototype in pixels, prove in steel.
And a contrarian wedge again. Reinforcement learning for dexterity could outrun supervised VLA once Simtorial stabilizes. Reactivity plus tactile feedback is underrated.
As long as don't lift with your back, lift with the math remains the motto. Safety first.
Speaking of safety, what's new and practical?
Multi-layer safety, semantic reasoning catches long-tail risks, physical subsystems halt collisions. New eval suites audit risk recognition, constrained pointing, and time to intervention in videos.
Auto-red teaming is huge. Attacker models craft adversarial prompts and scenes. Autorators flag hallucinations and unsafe suggestions. Automated feedback hardens the stack continuously.
Governance matters, explicit risk registers, incident reporting, and signed-off action constraints per environment. You want guardrails, not handcuffs.
Also, thinking traces improve interpretability. If the robot explains, grasp near rim to avoid spillage, operators trust it more and spot issues earlier.
Enterprise Rollout Playbook. Start with inspection and sorting, add pick and place with safe zones, introduce tool use gradually, audit success detection, instrument everything.
KPI-wise, track stability across visual changes, instruction paraphrases, and initial conditions. It's robustness by design, not happy path DMOS.
And keep humans in the loop for recovery behaviors. The robot can say bottle slipped switching hands like a sports commentator. Clarity reduces surprises.
Let's unpack orchestrator versus action model dynamics.
Orchestrator breaks tasks into steps, checks progress, calls tools. Action model executes short horizon motions. Decoupling is the clean architecture we needed.
One cool update: success detection in real time, even with moderate latency, thanks to predictive labeling. It's a rolling truth that stays relevant.
But watch the planning failure modes. If step goals are misspecified, execution will be flawless nonsense. Guard plans with verification prompts.
Complex pointing shines here. Points become trajectories, masks become boundaries. It's the paint-by-points heuristic for robots.
Recovery policies kick in automatically when unexpected states arise. Knocked bottle left, switch grasp. That inner monologue makes resilience visible.
Still, there's a ceiling to text-based decomposition. Hybrid graph policies with precompiled skills can cut latency and jitter.
Sure, but composability wins for long horizon tasks. You want Lego bricks, not poured concrete.
Current events, anything notable we should watch.
This quarter delivered new agent frameworks with tool use on video and audio, plus faster, embodied reasoning models that retain general capabilities.
Also, draft safety guidelines for workplace robots tighten requirements around constrained actions and operator intervention. Businesses should prepare for audits.
On the open source front, more spatial benchmarks emerged for pointing and progress understanding. Community evals will accelerate convergence.
And industry pilots reported strong results in mixed environments, retail backrooms, hospital corridors, and variable lighting warehouses. Not just shiny DMOS.
Cost-conscious teams are exploring smaller action models paired with strong orchestrators. Brains in the cloud, hands on the floor is viable.
Prediction time, tactile sensing plus learned recovery will outperform pure vision stacks. Feeling matters when everything's slippery and soft.
I'll add embodied agents will become the ops team for physical workflows. If good input, good output, then good sensors, great output.
Final takeaways, quick hits for tech and business leaders.
Invest in agentic separation and thinking traces for interpretability. Trust builds adoption.
Start with inspection and sorting. Expand to dexterous pick and place with safety constraints. Crawl, walk, run.
Build a multi-embodiment data strategy. Shared affordances compound learning across platforms.
Instrument success detection, progress estimation, and complex pointing. Measure what the robot believes.
Use simulation to rank options, hardware to validate. Prototype in pixels, deploy in steel.
Keep a hybrid pipeline and be ready to ditch overthinking when latency hurts. Pragmatism over purity.
And hey, teach robots to clean the coffee they spill. If they can do that, they're ready for prime time.
That's our show. Agentic physical AI is finally stepping out of the lab and into real workflows. Catch you next time. Up next, a brief summary of the key takeaways.
Narrated by the AI voice of Shri. The central question is how to build general-purpose robots that perceive, think, and act to solve complex multi-step tasks. The work introduces Gemini Robotics 1.5 and a companion embodied reasoning model for advanced physical understanding and control. Embodied reasoning means understanding visual, spatial, and temporal aspects of the world to plan tasks and estimate progress. Gemini Robotics 1.5 connects vision, language, and actions across different robots to execute instructions without robot-specific tuning. A vision language action model translates natural language and visual observations into low-level robot movements. Motion transfer is a training approach that aligns motions across robot bodies so learned behaviors can be reused between platforms. The model interleaves natural language thinking with movements, which helps it break down complex goals and act more reliably. Thinking here means generating short language traces before each movement to clarify objectives, failure recovery, and next steps. In evaluations, the model generalized better than earlier versions across appearance changes, instruction phrasing, and new starting conditions. Visual generalization means robustness to lighting, backgrounds, clutter, and textures. Instruction generalization means understanding paraphrases, typos, different languages, and varying specificity. Action generalization means adapting motions to new objects or initial states. Task generalization means succeeding on entirely new tasks in new environments. Training with data from several robots improved performance, and motion transfer amplified the gains. Skills transferred without extra training between a single-arm robot, a dual-arm robot, and a humanoid robot. For example, the single-arm robot closed an unfamiliar organizer after only seeing that skill on the dual-arm platform. The thinking mode improved multi-step tasks like sorting clothes by color by decomposing goals into short, precise movements. Thinking traces made behavior interpretable, revealing success awareness and self-correcting recovery plans when objects slipped. The embodied reasoning model achieved leading results on benchmarks requiring complex pointing, spatial understanding, and progress estimation. It retained broad multimodal skills while outperforming general models on tasks requiring grounded physical understanding. Complex pointing means predicting precise points or sequences on images or videos that respect physical and semantic constraints. It identified safe grasp points, avoided collisions, and used points as intermediate steps to count or plan paths. The system detected task success from single or multiple camera views and handled real-time decision-making. Real-time success detection means producing accurate success or failure signals quickly enough to guide ongoing actions. An agentic system coordinates high-level planning, tool use, and low-level actions during task execution. It linked the embodied reasoning model as the orchestrator with the vision language action model as the executor. An orchestrator breaks tasks into steps, uses digital tools like web search, tracks progress, and decides when to switch subtasks. In long horizon tests, the combined system achieved much higher task progress than using the action model alone. Tasks included sorting trash using online information, organizing desks from memory, packing suitcases, and cooking with dietary constraints. Failure analysis showed fewer planning errors, better success detection, and more reliable execution with the embodied reasoning orchestrator. A continuous progress score measured how much of a task was completed, not just whether it succeeded. The team adopted multi-layered safety, combining high-level safety reasoning with low-level physical safeguards such as collision avoidance. Semantic action safety means recognizing everyday risks, like heavy loads or slippery floors, and adjusting behavior to reduce harm. A new safety benchmark evaluated risk recognition, the effects of actions, and adherence to safety constraints across text, images, and videos. Automated red teaming generated adversarial tasks and scenes to expose weaknesses such as hallucinations and instruction obfuscation. Hallucination means the model inventing objects or facts that are not present in the scene. Automated judges critique responses and created training data that improved robustness to attacks. Despite improved generalization, dexterity remains similar to earlier versions and needs further research. Real-world testing is still necessary, even though simulated evaluations reduce the volume of hardware trials during development. Real-time success detection can be constrained by computation speed during fast, dynamic interactions. Motion transfer was less effective when the gap between robot bodies was very large, such as between humanoids and arm robots. Future work will learn from human and synthetic videos without action labels to address data scarcity. The team will explore reinforcement learning and new architectures to improve dexterity while keeping generalization strong. Reinforcement learning means improving behavior through trial and error feedback about success or failure. These advances could enable safer, more capable physical agents that help with complex tasks in homes, factories, and hospitals. Long horizon tasks are jobs that require many steps, memory, and sustained planning over time. Thinking uses extra computation while the model is making decisions, allowing it to reason step by step before acting. Longer thinking improved accuracy across embodied reasoning tasks, especially in image and video question answering. If this sparked useful ideas, share the episode with one colleague who'd benefit. Your signal helps us go deeper next time.